Welcome back. After having discussed different types of batteries and different battery characteristics in the previous videos, it's now time to discuss charge controllers in this video to conclude the important component involved in electrical storage in a PV system. As I said earlier in the batteries videos, the charge controller is principally concerned with the battery connected systems. The learning objectives are to understand the different functions that a charge controller can perform in a PV system. In addition, you will be familiarized with a couple of PV system topologies which uses charge controllers in them. So let's get started. The charge controllers forms an important part of the PV system. Particularly, they are important in the standalone PV system where battery storage is a necessity. In such a PV system, the charge controller is generally connected to PV modules. It is also connected to the battery and other loads of the system. So why do we need this component? To answer that, let's consider a simple PV system where the PV module is connected directly to the battery and no charge controller is present. When the sun intensity is constantly changing throughout the day, the current produced from the PV module will also vary. Because of this current fluctuation, the charging rate of the battery fluctuates and may, under some illumination condition, exceed the rated current of the battery, which would be harmful to the battery. To prevent this situation from happening, the device that is inserted in the PV system is the charge controller. Suppose in the same scenario when the sun intensity is very high, the battery will get charged very fast due to the PV module producing higher currents. When this battery reaches its full capacity, the PV module will still continue to produce current feeding them to the battery. At this point, the battery will begin to get charged beyond its capacity. This is called as overcharging of the battery. Overcharging the battery has a negative effect on its performance. It leads to several problems like gas formation, capacity loss, or overheating, thereby reducing the battery's lifetime. But with the help of a charge controller, this problem is avoided altogether. Here, the charge controller plays a vital role by decoupling the PV array from the battery, thus stopping the battery from being charged any further. Similarly, on the other side of the PV system, when the battery is supplying energy to the load during a period of low sun intensity, there will be a possibility that the battery might be fully discharged. Discharging the battery beyond a specific lower limit or over discharging the battery also has a detrimental effect on the cycle lifetime. Thus here too, the charge controller plays a vital role by preventing the battery from being over discharged. This is achieved by disconnecting the battery from the load. At this point, the system will not be able to power the load, but this is vital in preserving the battery. Another function of the charge controller is current regulation. Consider a battery which is being discharged at a faster rate than its nominal rate. This leads to a reduction in the efficiency of the battery as well. But a charge controller with a proper current regulator can be used to control this by maintaining the rate close to its C rate, which is the battery's nominal parameter. The charge controller does this by imposing limits on maximal current flowing out of or into the battery. Additionally, a charge controller also has a back charge regulator integrated into its circuit. This function is very useful, especially in a PV system that does not have any blocking diodes in its PV module or its PV strings. With the absence of a blocking diode, there is a possibility for the batteries to charge the PV modules when it's operating at low voltage. This means that the battery will impose a forward bias on the PV modules and make them consume the battery power, which leads to the solar cells heating up. A charge controller will prevent this situation from happening. In addition to current regulating functions of a charge controller, it can also function as a voltage regulator. Some charge controllers that are currently available in the market have maximum power point trackers included in them. With the presence of the maximum power point tracker, the charge controller can also act as a voltage decoupling device where the PV voltage and the battery voltages are decoupled. This allows for the PV modules to operate close to its maximum power point voltage and the battery close to its rated voltage range. Now that you know that a charge controller is meant to protect a battery in various ways, let's take a look at a few ways that this can be accomplished. You just saw that one of the main functions of the charge controller is to prevent overcharging of the batteries. There are two ways this can be achieved inside the charge controller. The first method is called the series charge controller. In a series controller, overcharging is prevented by disconnecting the PV array until a particular voltage drop is detected, at which point the array is connected to the battery again. On the other hand, in a parallel or shunt controller, overcharging is prevented by short-circuiting the PV array. This means that the PV modules work under short-circuit mode and that no current flows into the battery. Both of these topologies also ensure over-discharge protection. This is achieved by using power switches for the load connections, which are appropriately controlled by the charge controller algorithms. Finally, I will talk briefly about a couple of PV system topologies where a charge controller is used. As we know already, the charge controller is an important component in an off-grid PV system. So when deciding on the type of charge controller to be used, a proper decision has to be made for the right type of PV system. For example, when a system with only small DC loads are involved, the charge controller can be the component that brings together all the other system components. They are the PV modules, batteries, and the loads. Such a PV system is more common in very remote areas where the loads comprises of just few DC lamps and fans. The advantage from this is that a 12-volt system is enough to power those loads. Hence, it's relatively safe to operate because of such low voltages. Also, by using such a simple PV system, the cost involved is also less. On the other hand, when using a slightly larger PV system that also powers big AC loads, the inverter is also connected to the charge controller in addition to the battery setup. Now the loads are connected to the inverter. In such configuration, the system voltages may be 12, 24 or even 48 volts. You may notice that the battery is connected directly to the inverter here, not through the charge controller. This is because charge controllers may not be able to handle the high currents delivered by the batteries to the inverter. This means that the battery discharge protection that is generally available inside a charge controller is now available inside the inverter. This is sometimes accomplished by an automatic shut-off below a certain voltage, since the voltage drops with the state of charge. Thus, in this particular scenario, the charge controller will prevent only the overcharging of the battery, while the battery discharge protection is carried out by the inverter. So to recap, in this video we studied about the different functions that a charge controller can perform in a PV system. We came to know that in the standalone PV system, a charge controller is an important component that protects its PV modules and batteries from getting damaged and prolonging their lifetimes. They are also useful in getting an optimum power from the PV modules when maximum power point tracking is integrated inside them. With this, we have come to the end of the components involved in the electrical storage in a PV system. In the next video, I will discuss another very important component in PV systems: cables. So see you in the next video.